So let's start with an overview of virtual port channels, or VPC. You'll see in the illustration on the left that before VPC, right, with a typical spanning tree type deployment, we would have traditionally been blocking on one of our uplinks. What VPC allows us to do is logically create a topology where the two switches from a data plane standpoint act as one. So you can see here that the illustration on the left with VPC allows us to continue to have two distinctly disparate upstream switches, but from a downstream topology, logically, it looks as if it's connected to one switch. With VPC, we get a number of benefits. So with VPC, there are no blocked uplinks. We have ether channel load balancing to hash. It's a loop-free topology and lower oversubscription. VPC also does loop avoidance in hardware, right? So we can eliminate the use of spanning tree to make decisions about our uplink ports and eliminate block ports and unused bandwidth within our topology. So it's important for us to cover a number of topics related to VPC. A VPC peer is a VPC switch, one of a pair, right? So with VPC, we cluster two switches. So a particular VPC domain, which we'll talk about, is a cluster of two different switches. A VPC member port is one of a set of ports that form a VPC. So if we have a downstream device, this switch, that's connected to our upstream VPC domain, a VPC member port would be this port, let's say, one of the ports that connects to our upstream switch. VPC, again, means the combined port channel between the VPC peers and the downstream device. So that would, if we were referring to a VPC, we would be referring to this uplink collectively from this switch to these two switches. Now there are some items that make up the VPC domain between the two switches. The first is the VPC peer link. So this VPC peer link synchronizes the state between VPC peer devices and must be at least a 10 gig port channel, right? This link is also used to forward certain types of traffic, unicast traffic in the event of a failure, which we'll talk about later. It forwards multicast and runs the CFS protocol, which I'll talk about on the next slide. Next, we have the VPC peer keep alive link. This is sort of the heartbeat link that detects the status of the two VPC peer devices. So think of this as sort of the tiebreaker, if you will, as opposed to when we'll lose the VPC peer link. And we'll talk more about that as we continue through the lesson. So some other VPC terminology. CFS stands for Cisco Fabric Services Protocol, and it's used for state synchronization and configuration validation between the two VPC peer devices. Next, we have VPC VLANs. These are VLANs that are carried over the VPC peer link. And we have non-VPC VLANs. These are VLANs that are not carried over the peer link. And last but certainly not least, we have this idea of what's called a VPC orphan port. This is a non-VPC ports that are mapped to the VPC VLAN. So for example, if I had VLAN 100 running across my VPC peer link and I had a device here plugged into just one switch and that port was in VLAN 100, this would be an orphan port, and this ultimately would be an orphan device. And we'll get into more of what that means as we continue with the session. Now, let's talk a little bit about VPC loop avoidance. So VPC loop avoidance is data plane versus control plane loop control. VPC peers can forward all traffic locally, and the peer link does not typically forward packets. It's control plane extension, again, unless there's a downstream VPC failure. And the traffic on the peer link is marked and not allowed to egress, right? So typically, as the slide illustrates here, in an STP domain, if we had a spanning tree failure, this would ultimately lead to a loop on the network. In the VPC land, this situation does not exist because the data plane is actually doing the loop avoidance by marking traffic entering and exiting the switch. Now, as I mentioned earlier, the exception for this rule is for single-sided VPC failures. The peer link is used as a backup path for optimal resiliency. We'll illustrate that here. So if we were to lose one of the links from the switch to our VPC domain, we would be able to forward traffic across the VPC peer link and down a VPC port to the switch to allow that traffic to be forwarded again, only in the event of a failure. And now it's important to talk about VPC domains in general. So as I mentioned earlier, a VPC domain is a pair of switches, right? Now, each VPC domain is configured and uses a unique number. So in this case, right, you can see up here at the top, we've defined VPC domain 10 between these switches and VPC domain 20 between these switches. Now, VPC uses the VPC domain ID to automatically assign a unique VPC system MAC address. So it's algorithmic and it's based on the number. So that means that within a layer 2 domain, this could be even a layer 2 domain that extends across 2 data centers if you're using technology like OTV or VPLS to interconnect the 2 data centers and extend layer 2. This means that all the VPC domain numbers must be unique. We'll get into more about the domain number when we do the configuration for VPC. So some more of the VPC basics, right? As we discussed earlier, VPC peers function as independent devices as well as peers. We can see here that you can configure a switch to have a regular non-VPC port channel to one of the 2 switches inside of a VPC domain. Or you could use a VPC to connect one switch to both of the upstream switches in this case. It's important to note that when you're not using VPC, the local system MAC is used for all non-VPC PDUs, LACP, spanning tree protocol, etc. We'll talk about functionality that's been added to VPC called peer switch later on that allows for better STP convergence. Now, because we have 2 switches inside of a VPC domain, we must give each one of these switches a role. So the role's defined under the domain configuration. So you can manually define a lower priority to make one of the switches the primary switch and the other as the secondary switch. It's important to note that the role itself is not preemptive. So this introduces a topic of not only primary secondary, but you also have what's called a primary secondary, but operational primary and operational secondary, which essentially means that if I were to define this switch with a lower priority and make it the primary, and define this switch with a higher priority and it became the secondary, and this switch restarted for whatever reason or experienced some sort of failure, the switch on the right would be the secondary but become the operational primary. Right? So you must pay attention when you're looking at the status of the VPC switches for not only which one is primary and or secondary, but which one is operational primary and which one is operational secondary. In some of the output, if you don't see the word operational primary or operational secondary, you don't have to worry that it doesn't exist. It's just because there hasn't been a failure that's affected failover of VPC on the network. The other thing that's very important to know is that the role of VPC, who is the primary and who is the secondary, is very important when it comes to VPC failures. So in the example here, if we would have a peer link failure down here, I have a primary switch and a secondary switch, right? If the peer link were to fail, the way VPC operates to avoid loops in that case, right, and to avoid a split brain scenario that occurring on the network, is that in the event of a complete failure of the peer link, so not a single member, but a complete failure of the peer link is down altogether, the VPC secondary actually shuts down all of its VPC interfaces. So it's very important to know which switch on your network inside of a particular VPC domain is primary or secondary, because during a failure scenario, that switch is going to shut down all of its VPC interfaces. We'll talk about what that means for orphan ports and some functionality that was added to VPC a little later on in this lesson.